I should say, people online, if you can't hear us well, feel free to write into the chat box on GoToMeeting. And in the future, Jay or I will always be monitoring the chat box to see if there's any questions online. Today we're not doing that because I learned about half an hour ago that my monitor broke overnight. So we're using Jay's backup computer instead of the computer we plan to use. So anyway, so things are not quite as organized as they would be if we hadn't had a broken monitor. Yeah, so that I'll introduce myself. So I'm Jim Thorson. I was a PhD student with Andre Punt here in the fisheries department I finished about 6 years ago. And since then I've been with the stock assessment group at the Northwest Fisheries Science Center, which is just down the road. It's a federal fisheries lab. And for them, I've been developing spatiotemporal models to monitor fish populations, habitat, climate impacts, and associations between fishes. And I taught this class 2 years ago because I think that there's sort of a dearth of resources to learn about sort of modern spatiotemporal modeling. So, there's a classic textbook by Cressy and Weichel called Spatiotemporal Models. It's very dense. And for those of us who are not full-time statistics PhD students, I think there's sort of some of the computational methods that they develop are not really that necessary to learn, in particular because there's sort of an easy way to work up spatiotemporal models using Template Model Builder. And that's what the class will focus on. So I think that the niche of this class is sort of more applied work where people don't want to develop, a whole PhD on statistics and instead are focused on learning as much as they need to start doing new developments and new applications. Okay, and Jay, do you want to say anything more about your?
Yeah, I've been working on using this spatiotemporal model to apply to snow crab, try to understand how fish exchange over space and time. That's a project I've been working on.
Okay. Yeah, and Jay started as a professor at NC State, right, in August.
Oh yeah.
A few ground rules. So we've got these overhead mics on. I encourage people, if they ask questions, to project clearly, as I will try to model, because I think this room works well as long as everybody is kind of loud, but people off-site will have no idea what's going on if you don't talk loudly. We had maybe about 10 people registered on site, and then maybe about 25 people that had wanted to get emails to attend remotely. So it's kind of a big group. We'll be collecting homework from people. Here's where this not being my laptop is a problem. Is there some way to make this bigger? So the class meets Tuesdays 9 to 10:20 and Thursdays 9 to 11:20. And the longer Thursday lab session was based on feedback from students. When I taught it 2 years ago, a lot of students wanted extra time to go through code slowly. So on Thursdays, I'll probably come in with material, about an hour to an hour and 20 minutes of material. And then, essentially we can go slowly and go through questions in more detail on that Thursday. Jay will be doing a short kind of like applied example every Thursday morning, and but otherwise the Tuesdays and Thursdays, each class will generally involve some TMB code and some, maybe 20 to 30 slide PowerPoint. And all of those materials are online on GitHub. So could you raise your hand if you downloaded materials from GitHub prior to this class? Okay, so people will have to get familiar with GitHub during the class. I didn't tell anybody they had to download it ahead of time before this class, but people using Windows, I recommend the GitHub for Windows client, which makes it easy. For Mac, I don't know that much about what people should use. But the point of GitHub is that there'll be the PowerPoint up there as well as all the R code and TMB code that's associated with each class. We'll also put all the homeworks up there. The recordings will be available online at Google Drive in case people miss classes. And then in terms of homework, there's 4 homeworks that we'll be assigning, starting with the first homework being assigned this Thursday. Homeworks are due the following Thursday before the lab starts, and you're expected to email it into me and Jay. And we're only looking at homework from people that are registered for the class. So people off-site are allowed to send us the homework, but there's no guarantee that anybody will actually look at it to give you any feedback. You IHME folk, I know you won't register until 2 weeks from now, but if you plan to register, please start, doing the homeworks at the same time.
And I think we'll be able to register at the end of the week.
Okay, great. Okay, so there's 4 of those homeworks that are due, they're made of, I'll make available all the materials on the Monday before, for a week on the Monday before the lecture and lab starts. So for instance, the homework for week 1 is already available on GitHub, but we probably won't start talking about it until the Thursday of that week, and then it's due 1 week later. We'll send out a solution to the homework 1 week after that, which is about when nobody gets any credit left, and then you kind of lose the possible grade you can get on the homework declines each day, and it's written out in the syllabus in detail. Okay, so week 1 there's a homework, week 2 there's a homework, week 3 there's a homework, week 4 instead we ask for a 1 to 2 page description of a class project that everybody will be doing who's registered. Week 5 is the last homework assignment. And by week 7, I think, this might be subject to change, but I think by week 7 the assignment is to have a short script that can be used to generate the types of data that you were imagining using in the project. And then finally, by starting week 9 or week 10, we'll start having presentations. So the project has a presentation component where people will give maybe a 15-minute presentation on the project they've done, and then the written part of the project is due at the end of the class. So any questions about those sort of graded components? Okay, and it's all written in the syllabus, and in the off chance that I say something different than what's in the syllabus is what actually is right. I'm going off memory here. In terms of materials, we'll cover. Let's see. So, and how do you? So this is a PDF. Is there any way to view each page of the PDF on a Mac, or do I just kind of browse through it? Okay. Geez. So the kind of real kind of high level overview. Week 1 is a linear model, so it's a review of kind of basic stats and also getting people started on using Template Model Builder. So we'll be doing everything in Template Model Builder, and there'll be, I think, basically every week, every lecture lab and homework is involving that software. Could you raise your hand if you managed to install Template Model Builder ahead of time? Okay, and well, I think that was basically everyone. So I'm happy to work with people if there's technical issues getting it installed. And I think I sent out instructions for how to do it. It involves installing R tools. So I'm happy to talk to people later. Yeah, Grant?
You can just go to view full screen and it'll do it like a slideshow.
Okay. View.
At the bottom.
Slideshow. Enter full screen. I don't know what a slideshow would be then, but yeah. So okay, and then Week 2 is about generalized linear mixed models. So week 2, we're bringing in random effects, and that's what Template Model Builder is designed to do efficiently. Week 3, we do the first time series mixed effects model, so something like a Kalman filter, so a linear mixed effects time series model. Week 4, this is mislabeled. I'm sure I will have occasional typos. Because if it wasn't clear, I'm not actually paid by the university to do this, nor is Jay. So we're kind of doing it because we think it's important to do. So week 4 is on multivariate time series models. So models that have sort of 2 dimensions, one being time, one being multiple you're sampling. Then week 5, we start out doing sort of a similar thing again with 1D spatial models and how that relates to Gaussian processes. And also how to do these as sort of separable models, how to do these sort of in a computationally efficient way. Week 6, we start doing 2D spatial models. Week 7, we do space-time models, so models that have 2 spatial dimensions and a time dimension. Week 8, we do multivariate spatial models. And by week 9, either we do movement or maybe we'll do multivariate spatiotemporal models. It sort of depends. I mean, I haven't actually set up yet, but okay. So the point of it is to kind of go over the material in a couple different combinations, but the essential point is to be able to do construct models by hand that allow you to estimate spatial variation, how that changes over time, and how that could change for multiple categories, whether it's multiple ages of human, whether it's different size classes of fish, whether it's different species that are, competing with each other in shared habitat or whatnot. So any questions with any of that so far? Yeah.
So for the reading, should we just come to class on Tuesday having read those?
Yeah, I mean, so to be honest, I signed this class up with a class number, and we're required to put down readings. I think we spent some time thinking about the readings, and so I do encourage you to read them, but there's no tight integration of those into the class material.
Okay.
So I guess they're sort of encouraged, but there's no deadline that you have to obviously there's no test associated with any of this. So my philosophy is that on the one hand, we're all grad students. We're all kind of self-motivated to learn, and I don't, ideally everybody would get. I don't really care about the grading part. Again, not being a professor, I don't have to work to maintain the grading standards of any department. So my goal is to help you guys come away, with an interesting project that relates to work that you're already doing. And obviously the assignment on week 4, where people describe what the project is that they're doing, is our chance to give you feedback about whether it's ambitious enough or too ambitious, whether it seems like it's within the scope of the class. But that's the main goal. And the homeworks, originally I would assign homeworks and not grade them, and actually students came back to me and said that they wanted them graded as sort of a benchmark of whether they're getting as much out of the class as I expect. Those are intended more as a chance for us to give feedback, as long as people are able, basically keeping up with the class. I don't, my goal is just to facilitate learning. So, yeah, and then I wanted to say about the project. So, I'm excited about the projects as a chance. Well, I mean, to learn about what people are doing in oceanography and the forestry departments and IHME. And of course, as grad students, everybody has projects already in mind. But if anybody doesn't have a project already picked out, I think there's a lot of, publishable research in this field of spatial temporal models. So, feel free to email me and or Jay and start, reaching out with us to plan out what would be an interesting project. And I will point you to stuff that seems, publishable if you're interested in that. Yeah, so that should be a fun part of the class for all of us. Let's see, full screen. Or how does this? Do you know how? Is there a slide? Oh yeah. So the same way as a PC. Okay, so we went through the syllabus. Okay, so, and of course people have the materials on GitHub, and everything's all laptop based. So I kind of encourage you to, unlike, I've had professors that scolded me for Wikipediaing stuff or doing other stuff during class. I actually encourage you to have your laptop open so that you can kind of do whatever learning you think is most efficient. But I will kind of pose kind of rhetorical questions during the class, because I think that's sort of a useful way of making sure that people stay engaged. So if you want to, you're free to look at the slide ahead of time and actually get the answer I've written down. But for the sake of rhetorical learning, good old Socratic learning, feel free to not do that and just actually walk through the question with me. So first off, how do we typically estimate things? I think there's a zillion ways that people do learn from data. So maybe we can just talk about what are some of the ways that people have used.
Least squares?
Least squares, yeah. So I think does anybody know the story? I think Kepler was the first person who had these sort of satellite, had what do they call it, telescopes. And, people were looking at wobble of planets and stuff, and they'd take multiple measurements, and they'd just take, basically the average of different samples as a best measure. And there's some work that subsequently came out showing that if you minimize the least squares difference, it's sort of the same thing as taking an average. Kind of generalized, Kepler's method, the least squares. Other ways that people do?
Maximum likelihood.
Maximum likelihood. Yeah, so we're going to focus on maximum likelihood. So I've got a bunch of slides about why maximum likelihood is good. Other stuff. There's all sorts of heuristic kind of methods. I think there's about a zillion ways of estimating things. So there's emulators, and there's sort of non-parametric methods, and there's just estimators that have good performance but don't have any currently understood theory. Machine learning developed as sort of a series of estimators that only later did statisticians figure out what the statistical properties of them would be. But yeah, so in this model, we're focused on sort of maximum likelihood methods, and so it's essentially it's these sort of parametric methods in which you specify a model, you imagine, you use your creativity to come up with what's the process that could generate the data that you've observed. You then use that specified model to identify plausible values for any unknown parameters, which in maximum likelihood is equivalent to maximizing the probability of the data given your parameters. And then you assess uncertainty, hopefully. Actually, I think a lot of people don't assess uncertainty, but that's not us. And then we'll be using a lot of so this class is a little dry, I should tell people. This is sort of foundational kind of statistical methods. And what do you guys take for background stats in IHME? I don't actually know.
It's a huge, so we're in the global health department, so we take all the MPH classes, like biostats.
Cool.
Intro biostats is required.
Yeah.
After that, it's kind of up to us. Like we were both took a Bayesian class. I took a class on survival analysis last quarter.
Yeah, go on.
Now you're interested in.
Yeah. And forestry, what do you guys? Or I don't mean to put you on the spot. Sorry.
So there are no required classes, but like I've taken econometrics.
Okay. Yeah. I mean, it's so funny. I mean, I think again because there's so many different ways people estimate things. There's a lot of different ways people learn this material. So my kind of cartoon image of econometrics is a lot of sort of tests, like estimators that people have come up with, like sandwich estimators or whatever, that have good performance for a good, given situation, and so the theory is that some people might not have sort of all of the foundational concepts that we'll be building on in this class, hence the need to go over this slowly. Okay, so a function, we'll sometimes work with a multivariate function where there's many outputs from the function, and if there's a single output from the function, then it's a univariate function in GymLand. There's a lot of ways to define this stuff. And we'll typically assume that the input to that function x has multiple things, so it's a vector. So like a multiple regression has a single output but multiple inputs. Multivariate regression has multiple outputs and potentially multiple inputs. And then, given this sort of hand-wavy definition of a function, we also will be working with differentiable functions. So in general, we need to work with functions that have a first order and a second order derivative defined. Let's see, I think this is like, the Leibniz notation for derivatives, but anybody remember how are first derivatives defined usually in a calc book? How is this introduced to people?
It's like the absolute value of the slope as like the difference around a point sort of approaches.
Yeah, exactly. Yeah, so it's defined as the limit of the difference of that function as the difference in the x coordinate goes to 0, which is equivalent to the slope at a given point. And then second derivatives, people sometimes forget, not everybody's taken a multivariate calculus class, but really the only properties we need to know of a second derivative is that it's the change in the slope instantaneously at a given point. And that, the order of a second derivative doesn't matter. So if you differentiate with x1 first and then with x2, or whether you do it in the opposite order, you get the same second derivative. Any reminders about where like a second derivative might come up in estimation or optimization? Why do we care about second derivatives?
You're doing like Taylor series stuff.
So Taylor series stuff, it comes up a lot. Yeah, so in week 2, when we start doing mixed effects models, we'll talk about how we, that all depends on doing an integral across random effects, and that involves a second order Taylor series expansion. We'll come back to that. Where else might a second derivative come up during optimization?
You have like a local maximum or minimum. It's usually the second derivative is 0. So.
Exactly. Yeah. So we identify things that could be a maximum or minimum have a derivative of 0, and then the way you can check whether it's a maximum or minimum is whether the second derivative, the curvature, is negative or positive. So we have a maximum if you have a gradient of 0 and the second derivative is negative. You have a minimum if the gradient is 0 and the second derivative is positive. I can't think of any other kind of classic use. There's MCMC sampling and stuff, but I don't think we need to get into that.
For getting your standard errors.
Yeah, well, exactly. Yeah, that's a good point. So we'll come back to that later. Okay, and then I'll use vector matrix notation. So in fact, I try to force everybody I work with in fisheries to use this because it's not always been the standard. In general, I'll use italic to indicate a scalar, a thing that just has a single value. I'll use bold lowercase non-italic for a vector, and bold uppercase non-italic for a matrix. And then we'll deal with random variables using uppercase, not bold, not italic, and we'll use a tilde to indicate that the thing on the left. Well, this is actually bad notation already. So the thing on the left is a random variable, so this should have been C, capital C, not italic. And then on the right-hand side, we'll define a distribution. So in this case, this is saying that this random variable C on the left hand is following a normal distribution with a mean mu and a variance sigma squared. So we'll see a lot of it. If people are not used to this sort of tilde notation, I actually don't know the history of why this notation is used everywhere, but it's easy to program in it using JAGs, which I think is, JAGs and WinBugs, so I think that's part of its popularity. And it's, I think most statisticians I know use it these days. It's funny, I actually was not a quorum student, and my stats background is pretty ad hoc. So quirmies or others, feel free to object if you disagree with my summary of these basic principles. But again, a probability, I'll end up writing out like this. Other people have different notation, but I just write out PR for probability and use this to indicate that the thing on the left-hand side, well, again, this is me being kind of lazy. Really, it should be like capital Y is a random variable, and the probability that a random variable Y takes a value lowercase y follows a probability distribution. What are some properties of a probability density function? Anybody wanna? Integrates to one. That's there's only two that I'm really thinking about. And that's one of them. Yeah, and they're positive. Yeah. So the point is that this probability is saying that if you integrate this with respect to the random variable, that it integrates to one. And there's no negative probabilities that are allowed. And then a likelihood, by contrast, is just flipping these around and using a semicolon to indicate, again, kind of as a reminder that it's not a probability, but it is proportional to it's proportional likelihood up to some unknown constant. So, so what is this? So what does this mean? There's, of the two properties, one of them still holds of a likelihood and one doesn't.
Positive.
It's still positive, yeah, so C has to be positive. But there's no guarantee that a likelihood integrates to one. And so this comes up in Bayesian models all the time, where we've got these sort of missing integration constants that we have to work out numerically. But there's a bunch of methods that you can do that don't care about that missing proportionality constant. And that includes maximum likelihood. So like if you, well, I'm getting a little ahead of myself, but if you want to maximize, I'll come back to it. And then I think the final kind of theory background is, these sort of, well, I think there's a lot of ways to derive any kind of set of math, so I think this is sort of a sufficient way of defining laws of probability, although, some people think of conditional probability as an axiom, and I don't want to get into an argument with anybody who has a stronger motivation than I do for this. Okay, so we'll, throughout the class, we will do this over and over again, and what this means is that if you have a joint probability of two different random variables, you can factor it into the product of the marginal probability of one and the conditional probability of the other. And so this basically means if you've got a probability model that involves 1,000 random variables, you can always factor it into the probability of one of them, and the probability of the second given the first, third given the first and the second, and so on. So you can always factor a joint probability into a series of, univariate probabilities. We'll use that over and over. We will use independence a lot. So two random variables are independent if their marginal probability equals their conditional probability, and we'll use that in a second. And then the law of total probability holds that if you have a joint probability and you integrate out one of the two variables, you get the marginal probability of the other variable. So this one, for instance, is where we start seeing integrals, and integrals are used all the time in mixed effects models, and we'll come back to sort of what the common sense interpretation of that is later. Yeah, okay, so my definition of a linear model is this, where you have a predictor of some univariate response that's the product of some data x and some parameters b or beta, and then that response has a normal distribution, the data has a normal distribution around that predictor. So, why is this called a linear model? Anybody?
Because you just here the parameters are slopes, they're always straight lines.
Yeah, I mean, like I think the way we're used to seeing, the way it's usually derived is you've got like or the way we're introduced to it is, x's could be like, in fish, we've got a lot of models where it might say log weight is a linear model of log length. And so if you plot any prediction of the model of log weight against log length, it's a line. But, so why might that not be? Like the problem, of course, is you could put in any covariate and it's squared, and you end up with a nonlinear effect of something on something else. Anyway, I guess I bring this up because I think the distinction between linear models and nonlinear models is actually sometimes a little bit. I mean, there's models that kind of bridge between the two. You end up with a semantical argument. Anyway, we can come back to that later. And then finally, maximum likelihood estimation is where you say that a good estimator of some unknown parameters theta is the values that maximize this likelihood. So the definition is sort of in the name of it, and it basically, it involves it involves the first two steps of what we defined as estimating parameters. So the likelihood, the way you write out this likelihood, involves specifying a model that you think can generate the data given some unknown parameters theta. And then a good estimator for theta is just selecting the values that maximize the probability of the data given those parameters, which is equivalent up to a proportionality to this likelihood. And we'll talk about how you actually do this argmax, the maximizing of this likelihood with respect to the parameters theta in a bit. I'll skip y. So why do we actually use maximum likelihood? There's a few properties of it that make it a convenient estimator. Yeah, so one nice trick is that the maximum, you can transform these parameters and end up with the same maximum likelihood solution. So why would that be? Trying to think of what would be an intuitive reason for. I mean, we can kind of draw it out on the board, but Partly, I mean, it's just like that the maximum of a function, if you stretch the coordinates on the x-axis of any function, it doesn't change where the maximum will fall. So you can end up computationally, you can come up with many different parameterizations of a likelihood that will all have the same maximum likelihood solution. That's nice. It's not true of Bayesian models. I was thinking more of like what the statistical guarantees are of maximum likelihood as an estimator.
Unbiased, consistent.
Yeah, so it's consistent. It's not actually unbiased. Yeah, exactly. So so we'll talk about consistency for the correct model, or what it means to be consistent. So what does consistent mean?
Like approaches the true value as you increase the sample size.
Exactly. So under asymptotic arguments, if you asymptotically increase the sample size towards infinity, you are guaranteed to get the correct answer if you specify the model right, or the best estimator if you misspecify the model. And we'll talk about that more. What are some other properties of a maximum likelihood estimator? We already talked about one. I mean, John Best brought up that we can get, that if for lower sample sizes, asymptotically, given a set of data, that the estimates will be normally distributed around the true value. So we've got some guarantee about, even if we don't have large enough sample sizes to get a perfect answer, the estimate we are getting is normally distributed around the true value, which is nice. And John also mentioned that the second derivative is a measure of information, so that we can actually assess how well we are doing at our estimate. We can use the likelihood function itself to figure out approximately how far from, on average, how far from the true value we might be. I mean, if we repeated the experiment. Okay, so yeah, so that's what I'll talk about. So the consistency for a correct model, consistency for an incorrect model, and the asymptotic normality of the estimator theta. Is this stuff that people have kind of covered at this level? I mean, so maybe raise your hand if this is the first time you're seeing sort of somebody walk through maximum likelihood estimation. Yeah. Oh, okay. Well, so yeah, I mean, the hope is that this is helpful. I mean, I think this is sort of implicit in how people teach maximum likelihood a lot, but either, again, the claim of this class is that either these sort of claims are sort of buried in a lot of detail deriving this stuff, or there's a lot of classes that don't actually cover why we use it. And so, this class is sort of aiming to have sort of high-level concepts without really any formal derivation, so that we can use this stuff in applications. Okay, so consistency, as we defined it, it means that as the sample size n goes to infinity, then our estimate of theta hat, will go to this unknown theta true. And so to kind of get to that, you have to kind of bring in some notation. So say that we've got some true data generating process that governs the probability of some data y given some vector of unknown parameters, theta true. And then let's say you specify this probability model, and this should be capital PR. Well, this notation sort of sucks. This is taken from Gelman, the back of Gelman's Bayesian data analysis, and he uses different notation than I do, and so it's a little mixed up. But so let's say you specify some probability model for the data that, the true data generating process is not observed. But if you specify a probability for the data given some imagined model and some imagined parameters, then you can switch that around to get a likelihood. And you can use that likelihood to estimate the vector of parameters. And in a perfect world, you would have come up with a function. Your function P would actually contain the true data generating process, this sort of true in nature process for generating the data. Ideally is something that we could imagine on our own. And if that's the case, if we specify the correct model, which means that this true data generating process is a nested subfunction of the process that we specify, then as we collect more and more data, we are guaranteed to eventually get to the right answer. So that's sort of the theoretical basis that I think people use to imagine why this would be good. And what's the biggest problem people bring up with this theory? Or what would you imagine being a problem with this theory?
That assumption that your model includes the.
Yeah, I mean, so like ecologists like Burnham and Anderson talk a lot about tapering effects, where, you know, if we've got, you know, if I'm thinking about climate change in the North Pacific, you know, there might be 100 billion Pacific cod that are there, and so the true data generating process might be of dimensionality of 100 billion. You know, it might have a bunch of evo, like where rapid evolution is modifying how they behave. There might be this heterogeneity among individuals. There's all these interactions. There's all this habitat that we can't directly measure. And so in reality, it's really pretty silly to think that we ever can perfectly specify a function that includes the true data generating process, because the world is just way more complex than we have any real hope of understanding, I think. And so instead, you know what? Well, I'll say that so why, there's one case where I think this consistency with the correct model comes up all the time in what we do as scientists. So do people invoke this in their work ever? Or you see talks where people sort of implicitly invoke this claim? I think it comes up all the time in the fisheries department, at least, because we constantly are doing these simulation designs where we simulate data that we know the exact process that we're using to simulate it, and then we fit it with a model that often includes the process that we're using to simulate the data. And so if we do a simulation experiment, that's basically the only place where we ever actually see this consistency with the correct data come up. And a property of it is that if we simulate data and we fit it with the same model, we have infinite sample sizes, we are guaranteed to get the, you know, as we increase the sample size, we're guaranteed to get back the right parameter estimates. And why might that be useful to know when you're doing a simulation design?
Then you can see if your model is correctly specified, if you get the parameters you're expecting.
Exactly. It's basically like Andre Punt and I and others use it basically as a check on bugs. So, you know, like all students have this kind of game theoretic competition with their advisors to figure out, you know, the advisor's trying to figure out efficiently if there's a problem with the work, and the student's trying to efficiently show that there's not a problem. And one kind of, ecologically stable, stable distribution for this game theory, I think, is for advisors to force their students, when they have a project, to simulate data with the process that you use to generate the data, and show that as sample sizes increase, that you get the right answer back. So, and we'll do that in the first homework. If that is not the case, what is the conclusion that you make? You already said it.
Something's wrong.
Something's wrong. You probably have a bug. Because it's more likely you have a bug than that the statistical theory of maximum likelihood is wrong. Okay, and then the consistency for the incorrect model, which is what we actually care about for the real world, because we probably can't specify the right model. It falls back on this sort of callback Leibler divergence. So, assume there's some true data generating process. assume you've specified a model, a probability for the data given some parameters theta. There is, this theory says that there's some optimal estimate vector of estimates theta that minimizes the divergence between your probability of predicting new data and the set of and the true data generating process. And that optimal estimator, this is how you write out a Kullback-Leibler divergence. We'll never actually come back to this again. You can look this up later if you're interested in more details about the properties of this estimator. But in reality, what we're guaranteed with maximum likelihood is when we can't simulate, when we're not simulating the data, we're guaranteed that as we collect more data, that our theta will go to this optimal estimator. And this optimal estimator is the estimator that minimizes the divergence between predicting new data using our model versus the probability of the data given the true world, the data generating process. Anybody want to talk more about that? I don't really want to get too far into the notation, but conceptually.
Could you repeat the last sentence?
Yeah, I mean, so this divergence, this Kullback-Leibler divergence, is the divergence between using your model to predict new data, given your estimate of parameters, and the true probability distribution of new data that the world has that we can't directly observe. And as we collect more data, maximum likelihood theory guarantees that we will converge on that optimal estimate as we collect new data. And that's useful because it says, well, if we repeat a new data collection experiment under the same conditions, we always get the same estimator. That is the optimal estimator. It's nice to know that it's an optimal estimator, so it has a certain guarantee about being the estimator that best predicts future data. And then assuming there's an optimal estimator, which again is the estimator that minimizes this Kullback-Leibler divergence, and you specified a model, you've maximized the likelihood to estimate theta hat, then as n is going to infinity, if you replicate this estimator, the estimator will fall within some guarantee of, well, this is where people always get mixed up about phrasing frequentist experiments wrong. But if you replicated this experiment over and over again, your estimators would be normally distributed around the true value. So John, you started to allude to how we could estimate this theta, this sigma hat, and what were you?
Oh, well, you can imagine, you sort of imagine a likelihood surface, then it's got some slope at any point. It's also got the second derivative, hopefully.
Yeah. You
can imagine that a large second derivative means that the slope is changing quickly.
Yeah.
So it's going to be sort of a tighter surface. So that's called the information. So to take the inverse of that, that basically gives us a covariance matrix, which tells us how much variance there is in our estimates.
Yeah, exactly. So we can, the point of that is we can estimate what the sigma is in this guarantee. We can estimate it from the likelihood function directly. So not only do we know that our estimators, if we replicated the experiment, are normally distributed around the optimal estimate, but we know that from a single data set we can estimate this measure of uncertainty, and it's from the second derivative. And I'm not really going to talk much more about information matrices or functions than that. Okay, so so we already talked about this. So the consistency with the true model matters a lot because we're going to do simulation experiments a lot in this class, And if we do a simulation experiment and we are using the same function to generate the data and to fit the model, then as our sample size get large, the estimated parameters will go to the true values. And if your estimation model doesn't match your simulation model, if you intentionally are doing something more complicated where you simulate data using like an individual based model and fit it with a simplified model, then your estimated parameters will converge on a particular value as your sample sizes go up, and your total error will converge on an asymptote, where that asymptote is the Kullback-Leibler divergence. That's the sort of the measure of bias. You know, that's the kind of portion of error that's caused by misspecifying the model that is never eliminated by increasing sample sizes. So okay, so that was all the theory I wanted to get through today, and we've got about 25 more minutes to look through code. Is there any like 5-minute question for now, or? Okay, yeah. So and then the fair warning is that we don't. I think in my experience with the class last time, we don't always get through all of the code for a given lecture or lab, and again, as grad students, I kind of let you decide if you need to. You know, for some people that are new to template model builder or new to parameter estimation, that they have in the past benefited from making sure they go through that code outside of class later. And then others probably know this stuff already and don't feel like they need to follow up on it. But okay, so the code today will be, and it's on GitHub. Oh God. Yeah. Okay. How do you shrink the screen down, or if I would, sorry, Jay. Yeah, if I want to look at something else on this escape. Okay, and then I can, got it. So, as I said, all the material is up on GitHub. So if you click 2018 Fish 556, and you've got a GitHub client, you can click clone and open a desktop, and it will clone all of the code that's in that directory to your computer. Or you can do download zip and unzip it and get the code. You can also just click through on the website to see what's available. So like if you click week 1 and then go to lecture 1, I'll be looking at this .r file. .r means an R script. And raise your hand if you have worked with R before. Okay, so we will, for people who are not used to R, there will probably be a learning curve there, but it's pretty straightforward how it works. And then we'll also be using these .cpp files. So .cpp stands for .c++. And Template Model Builder is built using C++, but it builds in this automatic differentiation that we'll talk about at some point. I forget when. And so we'll be looking at those scripts in a second. So for now, we cloned that directory, and so we can see in this lecture 1 that we've got all the same files that are listed there. We've got this random tilde thing that's Microsoft Word saving a backup, and I don't know why it's there. We've got the canary histogram PNG, and here I'm just going to open up the .r file. And Jay's using RStudio here, whereas I'll be using just like TinR, which is a script, and just pasting into an R terminal. So in RStudio, we've got R code on the left-hand side, and then we've got an R console command line console on the right-hand side. And we'll look at that more in a second. So that 2 exercises today. One of them is just to try to figure out what's the mean density of canary rockfish in the California Current. So the California Current is this oceanographic region off Oregon, Washington, California, and up into Vancouver a bit, but we ignore that in the U.S. government. If we want to take the average, it's the same as taking a linear model with just an intercept. So a column X is a matrix with a single column where it has as many rows as the number of data points, and every value of it's a 1. So that's called that's an intercept in a linear model. And if you look at the 1 plus the log of 1 plus CPUE, or catch per unit effort for canary rockfish, we have some cases where we saw a CPUE of 8, a log CPU of 8. So e to the 7 is something big. We've got values of 1,000 kilograms per square hectare, which is the units of this data set. But for the most part, our data, 95% of our data is like way down here at less than 0.025. So we've got this really right skewed distribution to the data, and I'm not really talking about it too much. But we want to figure out what's the average of that across a certain specified domain. So if we're going to take the average, what are the ways that we might do that? Yeah, so you could just take the mean of it. Here, while I'm doing this, so the install in R install.packages DevTools is installing this package called DevTools. And then I use DevTools well, it's listed over here. So I use DevTools : install GitHub to install a package off of GitHub. So I put a bunch of code up on GitHub, and that code includes this canary rockfish data set. We'll see where it gets loaded later. The : means that install GitHub is a function that's distributed with the package DevTools. And I guess we could look it up. Install GitHub is basically saying that on GitHub.com there's a package called NWFSC assess geostatistical delta glim, and if we go to that, we can click on data, and we can go to West Coast Canary example.rda, and that's where that file is that contains these data that we're downloading. Anyway, so we loaded the package NWFSC assess : geostatistical delta glim, and then we loaded the package TMB. So remind me, it looked like most people had TMB installed, so I'll skip that for now. We then load the package. So this was back when I didn't really know package development very well. So I've got a directory called geostatistical delta glim, and that contains a package called spatial delta glim, where most people are smart enough to have the name of their directory match the name of their package. But I wasn't smart enough at the time. So we download this package spatial delta glim from that directory, and then we load the data using this command data. And then we can extract the CPUE, and this is just the code where I plotted it. We can always calculate what the mean CPUE is by just taking the mean function, like Kepler did back in the 1700s something. I guess that'd be a question for Wikipedia. So another method we could do is do a linear model in R. So in R, a linear model looks like this, where you type LM CPUE tilde1. And if we look at the estimate, 2.85, that's the same as just doing the mean of CPUE. we can also optimize this in R by specifying a likelihood function. So this function has some data, and it has a vector of parameters that I'm calling par, and it was called theta in the class lecture. Par is a vector where the first one is the estimate of the mean, and the second one's the standard deviation. So the way I'm writing this out, this is a vector. I just extract the first two elements by using this square brackets 1, square brackets 2. And then I calculate the likelihood of each observation by saying what's the probability of each data. This is vectorized, so it's this vector of data has a mean of the mean hat and a standard deviation of the SE hat parameter. And I say log equals true, so that means that it calculates the log likelihood of each data given that specified mean and standard deviation under the model that all of them are following a normal distribution with a single mean and standard deviation. And then the negative log likelihood is just the sum of the log likelihoods times 1. That's why we call it negative log likelihood. And then if we return that negative log likelihood, then we can just minimize that negative log likelihood, and that's equivalent to getting the maximum likelihood, finding the values of theta that maximizes the likelihood. So the way this looks, we run the function, we define the data as a list, that's the way it's built, and we define starting values, and if we, given those starting values of 1 and 1, the negative log likelihood is this number over here, and it doesn't necessarily mean anything because we're missing a proportionality constant. But the goal is to figure out what's the value of parameters that minimizes that negative log likelihood. And to do that, we can run this optim function. And so if we do that, we get an estimate of the mean and the standard deviation, and the mean 2.85 is the same that we've gotten from the linear model and the same that we got from taking the mean of the data. John, you want to walk through what this means again? I'm not.
So if you look to the innermost set of parentheses, you have ops dollar Hessian.
Yeah.
That's going to be our matrix of second derivatives. And then solve is the inverse. So you take the diagonal of the inverse. So those would be your marginal variances.
Yeah.
Take the square root to get your standard deviations, and then print them.
So this is sort of we're kind of again I'm not really going into the theory of why this is a good estimator of the variance of your estimate around the true value, but the point is that you can calculate what the matrix of second derivatives is of the likelihood function around your solution. You know the first derivatives are all 0 because that's the definition of a maximum or minimum. And you know that the curvature of that second derivative of the negative log likelihood is positive because that's the minimum of the negative log likelihood function. And we're just telling optim to calculate the derivative. And we're doing it because we're saying Hessian equals true. We're just telling it to calculate the Hessian, which is the matrix of second derivatives. We then take that Hessian matrix, we invert it, we extract the diagonal of that, and that's the estimate of the variance for each parameter, or the square root of that variance is the standard errors. And we'll talk more about what the interpretation of standard errors are later. Any questions with that block of code?
Seems like there's slight differences in the intercept between the 3 different methods.
Okay, let's see. Mean, CPUE, 2.84, yeah. 854, and what was the 854?
9, and then the one from the function is 8544.
Yeah, that's yeah. So I bet what's happening is that let's see, what would be an easy way to show this. So I bet what's happening is that our function in R is not, it's like the gradients are probably 0.001 or something. So it's getting really close to the solution. It's getting within 3 decimal places, and then it's just saying, okay, that's close enough. So what we'll see in the third way we're doing this down below, we'll do it in TMB, and we can show that in TMB has access to the gradients directly. And so we can get a much more precise estimate of TMB than we can by hand coding it in R very easily. One other thing we can look at here, well, that's weird. Oh, okay, square, yeah, okay. So that standard errors are this, 0.772 is the standard error for the intercept, and that matches 0.772 listed as the standard error in the linear model. So we're getting the same standard errors out of these, although we haven't talked about how to interpret those standard errors yet, but it's kind of nice to see the software is doing the same thing. We didn't get any standard error out of just taking the mean. So one benefit of using a model and writing it yourself is it's easier to extract summaries of the fit of the model. Any other questions about this? I don't really want to get too far into the R code for now, because of course we're going to do it in TMB in a second.
I don't know if it doesn't matter, then it doesn't matter. But why? I also haven't had like lots of data classes on MLE. Why do you only need the diagonal of the covariance matrix?
Yeah, so I mean the short answer is you don't only need that. So when people report a standard error in a model with more than one parameter, it's sort of sweeping under the rug a bunch of complexity. So if you, here's where I wish I had a better whiteboard. And you know, I used it. So in the future, I'll try to bring in this. I have this little sketch pad that I can plug into my computer and show people off-site what I'm doing. Is there any way, like, you have MS Word or something? I mean, MS Paint. I'm not sure how to draw anything on the board that people off-site would see.
Do it in like PowerPoint or something.
Yeah, that's true. Well, we've got 10 more minutes. Let's see if we can do a quick paint job in PowerPoint. Oh man, this isn't even my computer. I don't know how to do anything in this. And how would you, is there any way to like draw with a mouse in PowerPoint?
Yeah, if you go into the slideshow mode.
And
Click the current slide.
this is kind of fun. And then you, oh God. So I just clicked.
There's supposed to be, if you go, can you right click? With control click.
Well, this is a Mac.
Right, I think control click is a right click.
Is that like the, okay.
Do you want to plug this thing in?
It's okay. So I'm sorry, people off-site. The point of this is that if you've got 2 parameters, the Hessian matrix is a 2x2 matrix. If you invert that, you get a covariance matrix that's 2x2. And if that represents an ellipse, and from the theory we saw, we know that if we replicate that experiment, the estimate will fall within that ellipse around the true but unobserved value. And so a standard error, by contrast, is a way of saying what's the kind of distance that's likely to fall in one axis or the other. And if you ignore, you know, if it's a circle, you can do that really easily. But if it's an ellipse, there's no good way of, the standard error stops being a good measure of uncertainty for any given parameter. That's the short answer, without drawing anything. Sorry if that didn't make sense. We can come back to that later. Okay. So, okay, the TMB code. The third way we're going to do this is in TMB, and TMB works with R And the first step is you compile you do this function compile that converts this .cpp file to a .dll file or a .so file. DLL for Windows or an SO for Linux or Mac. And we'll look at the C++ in a second, but for now I just click compile. Okay, and then get working directory. Okay. I'll do that again. So so we click compile, and you have to have it pointing at the working directory of the C++ file. So like for this, in this case, this R terminal, if I type get WD, it tells me the working directory is at this location. And if I type list ls, list files, it says here's the files in the working directory, and so it sees this C++ file. And so if I do compile, it'll convert it to the same name, but .so. And because I've already compiled it previously, I already have this .so, and so if I try to compile it again, it just says make : nothing to be done for all, which is just TMB language for saying it's already compiled, don't tell me to do it again. The next step in TMB in the R side is doing this dyne load. So dyne load means you've got a dynamically linked library, and it doesn't really matter what that means too much, but you just have to tell R that it should look for this .so file that's called this. And once you load that SO file, it basically is setting up some memory on your machine to do some stuff in TMB. The next step is we make a tagged list called params and a tagged list called data. So a list in R is made by saying list, and the tag is the name. So params, we can kind of see, has two different elements that are tagged. And if we type params in the terminal, mean is a scalar with value 0, and log SD is a scalar with value 0, and data is a tagged list of all of the data, a vector yi with the data. So data yi just gets me a vector of all the data for Canary Rockfish. The next step in TMB is you build the object. So obj is now it's a tagged list that contains one slot. In R, if you have a list, you can type $. Can people see the screen okay, first of all? Is it zoomed in enough? So if you type names for any object in R, you can get a list of what's in that tagged list. And so the slots in this compiled object are par and fun for function, gr for gradient, and that's all you really need to know. So if I type obj par, it gives me the starting values of the parameters that I gave it. So params was a tagged list, and obj par is just saying those are the starting values that it understood that I was giving it. If I do obj fun, well, you can always do args to any function to see what the arguments are. So args obj fun is a function that has a single input x. And so if you do obj fun obj par, it outputs in this case, a negative log likelihood. We'll see the C++ code in a second. If you do obj gr, it gives the gradient of that function. That function has two inputs. X is a vector of length 2. And so the gradient of that log likelihood vector is also a vector of length 2 that says that the gradient of that negative log likelihood with respect to the first parameter is negative 21,000. The second one is negative 30 million. And you can use those. You use that objective function, the function, and the gradient, and you pass it to a function called NLMINB to optimize the function. So once you optimize it, it's saved in this object called opt, and the mean is this 2.854,934. So mean CPU. Yeah, so this one, doing it this way in TMB grant gave us, 85493, 85493. So it gave us 5 decimal places, even though the R1 gave up at about 3 decimal places. So we can already see that TMB is using the gradient information to get a little closer to the right answer.
Can we change that? Can we make it more precise?
Yeah, actually we can do, and by week 3 I'll start using what's called a function I built called TMB helper package optimize that you can get the answer to basically infinite precision. So like 1/trillionth of a gradient. So we'll talk more about that later. And then in TMB, the final thing I'll show on the R side is that you can get the standard errors by running this SD report. And the standard errors, the standard error of the mean, for instance, is 0.7723, which is about the standard error we saw before. Doing summary LM 7724. 7723. Okay, so we've only got 2 minutes left, and we haven't looked at the C++ file. And the C++ file looks like this. So I know it's a bad habit. Would it be okay if I go 5 minutes over? Or I will try to end on time. Maybe raise your hand if you have to leave exactly on time every day, or I promise I will not consistently go over. Okay, so the C++ file looks like this. At the top, there's this crazy gibberish. The first 5 lines I don't ever change, don't really matter. It's saying that it's a C++ file that needs to use this code in tmb.hpp, and I've never looked, well, I have looked at that file, but I don't ever change it. So the first 5 lines never change. The data vector, this is saying that the model should look for a vector of data called y sub I. And sure enough, if you do the names of the data that we pass it, the only thing is data y sub I. Where's the C++ terminal again? Sublime. Then it has these 2 saying parameter. So it's saying there's a parameter called mean and a parameter called log SD. And if you go to the R side, names params, it matches the mean and log SD. So, so we loaded in the data, and we've defined the 2 parameters. The objective, we then take this log standard deviation and calculate the standard deviation by exponentiating it. We can talk more about why we do that in a bit. We define the joint negative log likelihood and set it equal to 0. And anytime we do this in C++, we have to define the type of variables. And in TMB, we always just use type, capital T type. And we can talk more about that in a bit. But this is just saying I want a number called JNLL that is of type that we'll always use, and it's equal to 0. I can extract how many data points by doing y sub I dot size parentheses, that's C++ code. And then we do this loop where we loop through every data from 0 to n data, less than n data. This is a loop in C++. And we say that the joint negative log likelihood is subtracting off the probability of the data given our mean parameter, our standard deviation parameter, and it's true is saying it's the log from a normal distribution. So this has the exact same notation as the dnorm function in R, if you compare it later. And then we just return the JNLL. So that return is saying this is a function, and the joint negative log likelihood is this object called JNLL. So any functions about questions about this script? Any stuff that jumps out as particularly mysterious? We'll, again, every day, every lecture and lab will have at least one of these we look at and the homeworks. So I think people will get used to the notation for the most part. They'll all, there's always kind of special functions that are more confusing, but the main thing is this is a loop. We're saying we've got an int indicator that starts at 0 because C++ indexes from 0 to the end, and that's different from R. R indexes from 1, the last element, so that's one confusing thing. But this is a loop. This is saying that this is the log likelihood from the norm, and we're subtracting off that log likelihood to keep track of the total joint negative log likelihood of all data.
Is there any benefit to not vectorizing the objective function?
I forget if C++ vectorizes or not, or like the way it's done it, but the benefit of C++ code is it compiles it, and any modern compiler will see that it could vectorize it, and so in the back end it'll end up identical speed.
Oh, okay.
In R, because it's not compiled, you have to kind of be more specific about it. Okay, so that's all I wanted to do. There's another block of code down here where we then work through the same data set, but say what's the average density in Oregon, California, and Washington. And so if you are interested, please look at that before Thursday, because we won't pick that up again. If I really don't cover basic material, I'll pick it up the next class. And of course, on Thursday, we'll have extra time, so we can come back to it if people want. So that's it. Any final thoughts before we're done today? Sorry, Jennifer, I'm just seeing your comment now. Okay, if there's no other questions, we're good, and see you guys Thursday at 9.
Wait, why do you use just basic R instead of RStudio?
Well, before I answer that, Jay, do you see how I can turn off the recording? Let's do something. Well, okay, so I don't really have a good reason. RStudio used to like crash more. I mean, I think it's gotten better.
Okay.
I get kind of annoyed by having like the way it sets up windows and stuff. Okay, yeah, there we go. So if you click pause.